now I cover some other a bit smaller problems that you also face when doing machine learning for forecasting. So one would be this question, should you do direct output or iterative one step ahead? Right, so the idea is I have a time series, I want to predict the future. How do I do it? Do I just predict always the next point? Then I feed that back to predict the next point. I feed that back into my model to predict the next. Or do I build a model where I can predict directly a whole output window with many values? Yeah, so the traditional methods, ETS, ARIMA, they optimize just one step ahead accuracy. So if you need a longer horizon than one, they just iterate out. Yeah, so you feed back the forecast as inputs into the model. This can lead to error accumulation. And it's usually better to predict directly all the horizons that you need, right? Yeah, methods such as neural networks, they can have easily multiple outputs, so you have just an output window and that solves the problem. Other methods such as gradient boosted trees, they can produce only one output. So you now either iterate out as ETS and ARIMA, or you train a separate model for each horizon. And in general, if your horizon is very long, iteration may be the only feasible option, right? So if you say I have 1.5 years of data, but I want a forecast that is 2 years in the future, well, you cannot build, because in direct forecasting, your window needs to cover that, right? So if you say I want to do a direct forecast for a year out, well, now your input window needs to be like because you train with combinations of input and output windows. So now let's say my input window is 1 year. My output window is also 1 year. And it doesn't have to be the full year. You can say, even if you say I only want this last data point, 1 year in the future. Now, if you do direct forecasting, your windows are huge and you need big data sets to support that. Otherwise, you iterate out, right? If you say I have 1 year of data, I need a forecast 2 years in the future, well, you have to iterate. There's just no other way of doing it. Yeah, another interesting thing, the winning method of the M5, that was an ensemble of direct and iterative light GBM models. So sometimes people do that. They build both direct and iterative models, and then you use them both, and that sometimes works. Yeah, and now just in general, how to do gradient boosted trees for forecasting, because I guess when I say traditional classical machine learning, then that's what we're talking about. We're talking about gradient boosted trees. I mean, it could maybe also be feed forward network, it could be an SVM, but realistically, it will always be a gradient boosted tree. So they were very successful in several forecasting competitions. There was this JeffCom 2014, various Kaggle competitions. M5 competition was dominated by LightGBM. So LightGBM is a great algorithm. There's this other algorithm called CutBoost that performs ordered gradient boosting and therefore is especially suitable for time series. How do you do it? Well, you do seasonality and trend handling as I've outlined so far. You can then build one model per horizon. So seasonal and trend handling, you know, window-wise normalization, maybe some Fourier terms, things like that. So you build one model per horizon, then, or if the data set is small, you can have a feature that indicates the horizon. That's another trick that you can do with gradient boosted trees. So basically, if this is my input data set, and now I say, well, I want to have an output window, let's say of two values. Now, what you do is you can say, okay, well, I take the first one, I train a model, I take the second one, right? So my target, like my input data stays the same, but the target is 1 step ahead, or the target is 2 steps ahead. And now I build 2 separate models for it. Well, you can also just combine all of that, have an additional feature which tells me 1, 1, 1, 1, this is horizon 1, and then 2, 2, 2, this is horizon 2. And now I just build a gradient boosted tree over that, where I now give it as an input. Please do 1 step ahead, please do 2 steps ahead. The problem of that is that now your input data set is h times bigger. Right, so if you want to do 5 steps ahead, you now copy your training data set 5 times. So the data set kind of gets very big. So yeah, if your data set is not that big, you can easily build such a model. If your data set is already really big and you struggle to train your light GBM, then just build separate models. Yeah, then gradient boosted trees are especially suitable with diverse external variables. You engineer features such as rolling means, rolling standard deviations. You can use differences as additional inputs, you know, with different lags. You can do lag 1 difference, lag 12 difference. So I think the idea when using gradient boosted trees is always, yeah, so for example, with the differencing, you lose information. Yeah, sure. But you don't have to decide whether you put in the original data or the difference data. I mean, you can just put in all of it and let the gradient boosted tree decide, right? Because they usually do a really good job in feature selection. With neural networks, it's a bit different, but for the gradient boosted tree, I would always aim for a big comprehensive input data set where you do a lot of feature engineering and you just put it all in there together with even the original data and so on, and then you see if it what the gradient boosted tree does with it. Yeah, and then, well, you can do even further feature engineering. So yeah, holiday effects, you can have them one hot encoded. You can have distance maps of your holiday effects, you know, something like this is a day before Christmas, this is 2 days before Christmas, this is 1 day after Christmas, this is 5 days after Christmas, because that can have an effect. For monthly series, there often you have the problem that the number of trading days will be different for each month depending on where the weekends are or where Easter is and so on. So you can encode that as a feature. You will want to have promotion, like if you are a retailer, you want to have promotions in that, features, stock out events, prices, and so on. The weather is a very obvious feature. And then for all of those, the question is, you know, do I have lags of those? Do I do rolling means, rolling standard deviations over them? So then it starts blowing up a bit if you have all of these different inputs and then also do like long windows and other feature engineering over it. So there, sometimes you have to limit yourself a bit, but I think that's the idea. Yeah. Then another point, ensembling and forecast combination. I think the message here is ensembling works in forecasting just as well as in any other area. It's heavily used, for example, in Kaggle competitions. You see ensembles of gradient boosted trees, neural networks, pooled regression, even ensembles of local and global models. And yeah, like in forecasting, I think like ensembling is always a good idea, but in forecasting, you are sometimes surprised what you can do and works, right? Things like ensembles between, well, local and global models, but ensembles between iterative and direct models. I have a couple of papers where I talk with my co-authors where we talk about stability of forecasts, where you basically ensemble your forecast from last week and your forecast from 2 weeks ago for the same data point, right? So you make a forecast and you made that very same forecast for that same target date already a week earlier. And now sometimes it turns out that ensembling these two together works actually better than only using the newer one, right? People do things like let's train 10 iterations and ensemble that with the same model but train 3 iterations more. And it sometimes works. So yeah, like ensembling and forecasting, always think about it, and you will be surprised what sometimes works in that space. Yeah, and then I mean, ensembling from machine learning in forecasting is known under the term forecast combination. There's actually a seminal paper by Bates and Granger from 1969, so a lot earlier than when machine learners thought about ensembling. In that paper, they show that combining forecasts often leads to better accuracy. It's widely accepted and adopted in the forecasting field since, and usually in forecasting, the idea or what people usually think is that simple average, or what people usually find is that simple average is hard to beat. Many more sophisticated methods exist, but it's always difficult to beat just a simple average. Yeah, so, well, because we've now talked a lot about traditional machine learning methods and what they implement or what they should implement to do certain things, deal with non-stationarity, deal with different horizons, and so on. Here I put you some software implementations. There's this very nice implementation, ML Forecast from Nixtla, where they put especially effort into having it scale well to large data sets, right? So most of these frameworks that I put you here are basically just wrappers for light GBM to implement all of these things that I've now talked about, the Fourier terms and the multi-horizon forecasting and some trend handling and so on. So yeah, ML Forecast, as far as I know, it's purely NumPy and compiled and so on. So they really try to make it fast. Then SK Forecast, I found that a very nice beginner-friendly implementation of such a wrapper of traditional methods. Then, well, one that I want to mention is the CUTS library, developed by Meta. And so they have a light GBM wrapper in this ML AR module, and that's actually one that I implemented. So it has all of the functionality that I talked about here. And it's also, I also try to make it scale well. And, it would even do things like, because if we now say, okay, well, we have to do, you can either do iterative forecasting or you can do direct forecasting. Well, you can also mix the two, right? So you could train one model. So for example, I told you, well, you can have a light GBM and now you can have an indicator feature which tells you for which horizon you train. Well, you could have that for a horizon of, let's say, 12. Okay, so you have 12. You have 12 that you model directly, and that's your model, a direct model. But if you now say, oh, but actually now I talked to higher management and they told me they don't want 1 year, they want actually the next 3 years. Okay, but I already trained that model well, so you just use that model and roll it out. So now basically you feed these 12 predictions back, and now you get the next 12 predictions, right? So you can even mix iterative and direct. Or you could also do things like, well, I predict a horizon of 1, 2, and 12 on a monthly series. And if anybody ever tells me, well, what about horizon 7? Well, now I just roll these ones out, right? So you can also mix direct and iterative. And that's something that, for example, this wrapper does. I'm not sure if the others do it, but yeah. Okay. That concludes the part about the traditional machine learning, and the next part is now deep learning and foundation models and so on. Thank you very much.